Morning, everyone. Today will be the start of a new chapter. If you look at our course so far, we started looking at kinematics, so studying motion concepts, velocity, acceleration, displacement. We then applied it in chapter 2 with forces. We learned from Newton's second law that if you have forces, forces aren't needed for motion, but forces are needed for acceleration, for speeding up and slowing down. We switched over quickly to look at momentum and energy. Momentum has this notion of it being conserved. All the momentum before the collision has to be the same as all the momentum afterwards, and we saw how that interplayed with energy afterwards. This last part here sort of wraps up a little bit of the motion concepts and gets us into a few sort of other side topics that we're going to get into to finish off our course. In this chapter here, we're going to mainly look at waves. We'll still make a few connections here and there with the older stuff. We'll see in this lesson here how period and frequency comes back again. But aside from those connections, just treat this as just a fresh new page, a brand new chapter. So let's start off here with our main concept here. We're going to have a look at a waves, or what is a wave. Waves are defined as a disturbance. Okay, it's a signal, a disturbance that travels through space. But unlike the kinematics that we've been doing, there is no what's called permanent displacement. So without permanent displacement. So let's just do as a quick analogy here. Let's imagine we have just two people just standing there, right? So back in our kinematic section here, we had objects. We can throw objects around. So let's say the person on the left here has the object. He can physically toss the object over, maybe a football style question over. In that case there, you've been able to move something. We can call that a disturbance. You've been able to cause something to travel through space. But in this case here, there's been a permanent displacement. At the beginning, the D initial is with the guy on the left side. After the ball gets tossed over, the DF is now over here. There has been some permanent displacement. There's been some permanent change in the position. In terms of the wave stuff that we're going to talk about, we can have the same two people. Let's imagine this time I've stretched a long slinky between them. And let's say they're just holding the slinky, it's just sagging down this way. It's possible for you to actually send this disturbance, send this wave down without an actual permanent displacement. So I see if you can just picture this here. Imagine the guy on the left side is just going to do a quick little pulse. He's going to move his hand very quickly up and down. That's going to cause, so the wave initially, if the slinky was sort of held taut, it should be straight across like that. That's going to generate a pulse. And what's going to happen to this pulse is going to end up just traveling down the line. The wave particles themselves actually only travel up and down. Every part of it just travels up and down. And yet somehow this disturbance, this message or this signal gets all the way from the left side. It hits the friend on the right side here. Let's say the person on the right side here holds his end fixed, so holds the slinky tight. And we can actually watch this pulse here travel all the way down on the one side here. It's going to reflect on the other side here, and it's going to go back the way it came. In this case here, there's no permanent displacement. The person that's holding the slinky here on the left side is still holding on exactly the same part of the slinky, even though the signal was being able to pass sort of left and right here. The particles were not permanently displaced. So in this case here, this is sort of the notion of waves. We'll get into the phenomena in the next lesson, but basically here for waves, it doesn't have this permanent displacement. You're still physically holding on to that portion. So what is the job of a wave then? What is the job of this disturbance sending back and forth? The function or the job of this, the function is to transfer energy, is to transfer this message, is to transfer this signal from one place to another. Right. So we talked about a couple features of waves already. Waves have no permanent displacement. It's not like the object is physically pass from one place to the other, but really the goal of this is to move energy from one place to the other. For this starting lesson here, I just want to introduce to you some of the vocabulary. So there's a lot of terms for us here. First thing, we're going to categorize two main types of waves. First type of wave here is going to be referred to as an electromagnetic wave. Electromagnetic wave. If you go on into physics, you're going to learn that light is actually made out of alternating electric and magnetic fields. That's why we call it an electromagnetic wave. Sometimes we refer to this as an EM wave. And again, as I just mentioned here, light would be a good example of this electromagnetic wave. for this sort of classification of a wave here for electromagnetic waves do not require a medium to travel through. So what I mean by medium here is a sort of a background material. So is the background material water? Is it air? Basically here it's what the wave is going through. So what I want to be careful here is, let's say we take the sun as an example. The sun is giving us all sorts of different energetic waves here. It's going to shine a wave here. That energetic wave here, that EM wave here, is traveling through the nothingness of space. So now you refer to space as a vacuum. There's actually no particles there. That's actually a little bit of an oversimplification. There is the odd particle. It's not much though. You can pretty much imagine that as emptiness. And yet this one here as a electromagnetic wave has no trouble. The light and the warmth from the sun here has no trouble getting to us. Right? So its function here, as we see, is to transfer its heat energy from the fusion reactions, transfer energy from the sun to the earth. So we feel the light and we feel the warmth. Careful in the definition here, it says it doesn't require a medium. It doesn't mean that it can't travel through medium. So let's say this light wave here, it's just traveled through a vacuum, practically nothingness. Now it enters our atmosphere. Our atmosphere is made out of more dense particles like nitrogens and oxygens and whatnot. The EM wave here has no trouble traveling through medium. It's actually it doesn't need this medium. It can travel through a medium if it wants. We're going to see in a later lesson here, in traveling through different medium, it's sort of running into other particles. Depending on what type of material it's trying to cut through, the speed of the wave actually might drop. We've learned from our sort of junior science courses here, light from the sun is actually given to us as white light. It's a whole combination, it's a whole spectrum. So let's just recap here this EM spectrum. Turns out the visible portion of light is actually a really only narrow region. We're going to call that the visible band of light. We're going to have the one end here, which is the red end. I'm going to roughly shorthand that 700 nanometers. I'll talk about what that number is in a second here. So the red side is the 700 side. The purple side here is roughly the 400 nanometer side. And in that case there, the visible spectrum takes us from our Roy. If you have colors, you can just sketch this out for yourself. So Roy G. Biv. Again, I haven't explained to you what these numbers are just yet, but we sort of have that spectrum. What I want to show you here is those are the parts of the light that we can see. When these colors add up, this is what amounts to white light. So white light is the entire Roy G. Biv. It's not just going to be strictly 700 and 701 is not. It's just giving us a nice ballpark number. Turns out light actually exists as a much larger spectrum, parts of light that would just appear to us invisible. There's 3 different types of light that are more energetic, 3 different lights that are less energetic. Let's do the more energetic ones here first. If we go beyond the violet region, we're going to call this region here ultraviolet. Ultra meaning beyond, and we're sort of pushing past the purple end. This is what we usually call UV radiation. This is what sunscreens are supposed to protect us from. So more energetic light. If we keep going beyond, keep getting a shorter, this number here later on we call the wavelength, we get into X-rays. X-rays here are at first they were unknown, that's why they called them X-rays. But X-rays here can travel through soft tissue, no problem. So let's say you are in a car accident or something and you want to actually make sure you have no broken bones or whatever, the doctors might put you through an X-ray machine. The X-rays are energetic enough to pass through your muscle and different tissues in your body, and it will actually reflect off bones almost like light off a mirror, and by tracking where all that reflection goes, it can actually give you a nice scan of the bones underneath. As we get farther beyond X-rays, we get into gamma. The symbol for gamma is like this fish that sort of went downwards here, but this one here is gamma radiation. We really only see gamma radiation deep in space with pulsar stars. Pulsar stars are constantly rotating, and because of that rotational motion, it tends to give off gamma radiation. In sci-fi, if you like Incredible Hulk, Incredible Hulk was radiated by gamma radiation. Basically, the way I pointed the EM spectrum here, we're getting more and more energy, so high energy towards that side. They're not all evenly spaced, but at least I have the 3 categories above. We also have 3 categories below that are, again, not evenly spaced. On this side here, we're going to shorthand it IR radiation. When I look at the word here, I always want to say infrared, but how we read it here is we're going to say infrared. So infrared IR. This one here is sort of useful for thermal imaging. If you have any like night vision goggles and you have like hot objects glow a more yellowy orange tone, that's the infrared radiation. Without the goggles sensing that radiation, it's invisible to us, but infrared goggles is sensitive to a little bit lower energy light. It's into the red, so that's why it's on the reddish side. Then we have our two last categories here. We have our microwaves. So microwaves, we know it's low energy because we know we're farther down along the spectrum. Microwaves are the perfect amount of energy that water particles like absorbing. Water particles have polar bonds, so if the energy is perfectly the right energy, the water molecule here starts shaking around a little bit harder. Microwaves are used to heat up the water inside your foods, and we sample it here as a hotter substance. So that's what microwaves are, and then we go beyond there. Again, there's no really clear overlaps between when we cross over one to the other. They sort of mix into each other, but roughly speaking, if you get really, really low energy, we get into those radio frequencies here. The second you turn on a radio that's sort of tuned to those energies, you suddenly hear your broadcasters. That means the radio waves are constantly around us. Without our radio actually sampling either AM or FM sort of modulation, those sort of frequencies, we can't hear it. It's otherwise invisible. So all EM waves here, they're called EM waves because they don't require medium to travel through. They can travel through material, no problem, but in general, when waves travel through material or media, they tend to slow down, and that will actually cause some bending in a later lesson. So we have higher energy here. Even though all of these are actually forms of light, the thing that keeps them together is all of these forms, all light travels at, of course, you can call it the speed of light. Well, light travels at light speed, okay? But this one here is actually given to us as a constant. We usually use c for it. C implies that we're traveling through nothingness, vacuum. Again, it's going to be the fastest if it travels through nothingness. And the speed of light here is given as a constant 3.0 times 10 to the 8 meter per second. If we get around to it, we're going to find that a lot of our Newtonian physics, the physics that we've been learning so far, they get thrown out the window by the time we get to such fast speeds. We have time starting to slow down. We have masses starting to increase. Things get all really funky. But in this case here, we're just letting light do it. Light is actually a sort of a constant speed here. We traditionally would think time is a constant. So my clock here reading 10 minutes would be the same as your clock reading 10 minutes, no matter where you are, no matter what you're doing. But we're going to actually find that in our universe, it's actually the speed of light. This number is actually a constant that actually makes time slow down as the objects travel faster. Again, in our everyday physics, we actually don't experience this because we're nowhere fast enough. This one here is talking like millions of meter per second, like tons and tons of speed. So, so we're getting to that relativity section, possibly towards the end of this section here. But all of those forms are forms of light. So be it radio waves, which are invisible to me, UV radiation, gamma radiation, which we don't really see here, all light rays will travel at the speed of light. However, they carry different amounts of energy. So we're going to come back later on. We're going to define what was the 700, 400, and how do I show that waves actually carry different amounts of energy. Just before we get to that here, I want to give you the second type of wave. First type was electromagnetic wave. The second wave is called a mechanical wave, like mechanical energy like we did in the last chapter here. A mechanical wave like sound would be a good example of this. Mechanical wave, earlier the EM waves here didn't need a medium to travel through here. Sound actually does need a medium. So this one here, physically, it requires a medium to travel. As you're listening to this here, or if you listen to someone talk, you're actually hearing the energy that's leaving a person's mouth. It's actually vibrating through the air particles in between their mouth and your ear. And basically, as those air particles vibrate through, they're actually transferring that energy. They're transferring that disturbance, that signal, so that you can hear what the person is saying. So it requires me to travel through, which means that, let's say out in space again, when there was nothingness, when there was a vacuum, there's no particles that are actually vibrating in between, let's say, two astronauts. You can yell all you want, you actually won't hear each other. It's only on the Earth's surface here because there naturally already are air particles. It's like that slinky is already stretched in between you. You can just trigger the air particles, cause some disturbance to the air particles. The air particles do the vibration for you, and it will transfer that wave. Without the slinky, there'd be no way for you to actually hear anything. So, mechanical waves here, sound energy, we need those air particles. These mechanical waves here can be further subdivided into two types. These are important words here. Waves can either be transverse waves, or waves can be referred to as what are called longitudinal waves. Longitudinal waves are also sometimes referred to as compressional waves. So compressional waves. Both of these are types of mechanical waves. Both of these need particles to actually carry their energy through. But in this case here, I want to specify here which direction the particles are actually moving. For transverse waves, the metaphorical slinky here, the particles travel perpendicular to the wave. So imagine you were standing here, imagine you were standing here. We have our slinky. This time I'm going to pull it taut, so it's just sort of tight on both ends here. What I'm going to do is, instead of just doing a quick up-down motion and sending a pulse that travels downwards, what I'm going to do is I'm going to oscillate this backwards. The word oscillation just means rocking back and forth. I'm going to constantly move my hand up and down like this. Shouldn't really surprise you here. We're going to end up with this sort of shape. Now, of course, depending on what your other friend is doing, if he's holding it fixed or not, it might reflect in different ways, but over time you should get this sort of motion. We have the wave that's actually traveling down the distance. So the wave is actually traveling from left to right, going across. If I put a piece of tape on any part on the slinky, I'm going to realize, like we said earlier, there is no permanent displacement. This piece of tape here will mark a particular part of the slinky. As the wave travels back and forth, this particle is actually just rocking up and down. It's traveling perpendicular. It's in the up and down motion relative to the wave that's actually traveling downwards. So a wave that does this is referred to as a transverse wave. What's the other type of wave that's possible here? Longitudinal wave here is, what if my particles are actually going to be traveling parallel to the wave? So same analogy, sound wave is actually an example of a compressional wave. So you can imagine sound waves doing this. Again, I'm going to have my slinky that's just taut here. This time, instead of doing a rocking motion up and down, I can even do left to right. I can also do a transverse wave that way. But this time what I'm going to do is I'm going to contract the slinky. I'm going to tighten the slinky more than it wants to be. Hooke's law would say it wants to restore itself. And as I let go, what's going to happen is the particles are going to rock back and forth this way. The signal is still going to be sent down the length of the slinky. You're going to see parts that are wider separated, parts that are more together. And we basically have waves that are pushing back and forth. That same analogy here, using a piece of tape here, marking off a part on the slinky. This time we are actually going to be paralleling. The wave is supposed to be traveling back and forth between these two partners here. The particles never permanently get displaced, just like we noticed for all waves, but the particles here, depending on if it's in the compression part or depending if it's on the stretching part here, it is actually traveling parallel to motion. This is actually what's happening to air particles between. So the air particles are like that metaphorical slinky here. As you actually talk, what you're doing is you're causing the air particles to bunch up in some places, to stretch out in other places. That signal is sort of pushed along. You can even imagine holding the slinky or air particles and pushing back and forth along the slinky, definitely parallel motion, but somehow getting that signal from your mouth over to the other person's ear. So without air, without a medium to travel through, neither a transverse wave or a compressional wave would actually do anything. So, lots of definitions so far. We talked about waves. The function is to transfer energy from one place to the other. We talked about some waves not needing any background, like light. Some waves definitely need a background, like sound waves. So, here's a few last definitions for us here. In sort of addressing that problem, well, how do I know if the energy carried by the wave is a lot or very little? What are some things I can measure for waves? Here are a few different definitions. And these definitions can be applied for both the EM waves and the compressional waves. So we're just separated a section here with definitions. Let's imagine I go down to the ocean, and let's imagine I take just a still shot. Waves do what's called periodic motion. So waves, whenever you see that word period, it means something that repeats. So something that's periodical, like periodic table, it's patterns repeating on the periodic table. It's periodic motion, it's things that repeat. So back with my analogy, I'm down at the ocean. I imagine I get down to sea level and I take a still shot of waves. This time it's water waves on the ocean. And let's say the waves on my picture, first thing, it may not be nicely symmetrical like that, but imagine I'm taking a still side shot. This is a side view photo of the ocean. So definitely waves are periodic in motion. The waves come from really far away. This is out in the ocean. This one here might be closer to shore. The waves are transferring that water energy here, sort of from ocean to shore. The waves themselves are transferring this energy. In this case here, would this be a transverse wave or would this be a compressional wave? Again, with the metaphorical slinky here, if I were able to track down any given water particle, what's going to happen? Actually, let me just start it a little bit lower there. Let's imagine I actually started off right here. So this is a still photo taken at t equals 0. A second later, the wave would have pushed in. So as the wave pushes in, I'm going to color code it here. The wave pushes over a little bit. Okay, it runs into shore. That particle that I tagged will actually have just traveled upwards. You'll notice this part here is perpendicular to the wave motion. Hopefully you were able to say this is a transverse wave. Again, a second later, if you have colors, you can color code it for yourself here. Let's say the wave pushes to the top. The wave just keeps pushing along. Again, as time goes onwards, the wave just keeps pushing past you. And then you basically, that point in space will just rock to the top. And then as the wave pushes even beyond you there, you're going to end up following the wave downwards, and you're actually going to rock downwards. As you do that motion, it shouldn't be surprising to you. You end up rocking up and down. If you were on a boat, as the waves pass you by, the waves are constantly going ocean to shore, but as a wave, give or take a little bit of motion, just sort of side to side, you are pretty much rocking up and down. So that's my wave so far. Let me just redraw it so it's a little bit easier. So this is a still frame. This is at one given time, my wave, maybe it's pushed on a little bit here, right? It's not necessarily going to be always lined up nicely. What we're going to define is a couple of terms. Every top part of the wave, we refer to these as maxima. This is the maximum that your water wave peaks at. We're going to call these maxima here crests, or like we said, maxima. They're the maximum that these waves here are actually up at the top. On the bottoms here, we can refer to them as troughs. It's like a pig trough, so troughs. Troughs are going to be minima. Those are the absolute lowest points, minima. All right. The absolute maxima and lowest point here are always measured as relative to the no wave case. If we were a still day where there's actually no water waves rocking, sometimes you refer to this as the equilibrium position or the rest line. Basically, if there's no wave, there would be no maxima, there would be no minima. In this case here, now that I have those three, I can actually measure how far is the maxima away from the starting line, or how deep is the lowest point here from this maximum line here. We call those distances there, we call them the amplitude. Amplitude is a measure of energy. In the sound wave example here, the amplitude would give you volume. The bigger the amplitude, if I had a bigger wave like that, that would just be a louder sound. The amplitude is, as I've labeled, the distance between that equilibrium rest line and the crest or trough. Amplitude is always a positive number. It's always a positive. I use the term distance, so it's scalar, so I'm not going to have positive or negative, even though I know this amplitude is above and this amplitude is lower. So that's amplitude. That's a measure of energy. Because waves repeat itself, it may be a little bit more clever. Instead of actually tracking, well, how far did this wave actually travel going from ocean to shore? What we're going to do is we're going to instead just look for parts before the wave repeats itself. So you're welcome to start anywhere. Normally I would actually start off, I'm on the equilibrium line and I'm just about to go up. This wave here goes up and down and then comes back to that point there. We see that if I just copy and pasted this segment and I just sort of copy and paste it over, I basically have an exact copy of the next unit of the next unit of the next unit. Instead of giving you the actual length that the wave travels, I'm actually going to refer to this as your length of the wave. So in that case there, as the name suggests here, we're going to call this the wavelength. It is the length of the wave. It's not actually the length that the wave actually travels, but it is the length before the wave repeats itself. So wavelength is the distance before the wave repeats. Right? It's the distance that you can copy and paste to get the next unit down the line. Usually for wavelength, just for simplicity, we're going to actually use, well, it's crest to crest or trough to trough. Where that actually comes from is sometimes it's a little bit hard to actually track where is that equilibrium line, especially as these waves are rocking past. Sometimes when we're on the equilibrium line, oh no, that's only half the wavelength. We haven't repeated yet. It may be a little bit more easy to just say, well, this is the crest, this is the top, this is another crest. Well, you would have to have gone down to the equilibrium line, to the trough, back up, and then back up to the crest here. That distance there in brown should be the same as the distance in blue there. Surprisingly, we use a symbol lambda. It's like a, I don't know how you describe it, it's like a squiggle kind of letter there, but that defines for you distance, and because it is a distance, it should be meters. It's the distance for it to repeat itself. It doesn't have to be crest to crest. You could have similarly done trough to trough, and that way there it would also be wavelength. Earlier when I had given you the numbers 400 nanometers and 700 nanometers, that actually was a wavelength. So if you imagine here a red photon, if I had a red laser pointer, so for example, red light, I'm going to give it to you as roughly on the 700 nanometer end. So red light as your laser, you can think of red light as just a stream of photons. The photons are just exactly like a laser pointer. They're just carrying energy from your laser pointer to wherever you're shining it. Light actually does travel in a straight line, but to represent light as a wave, I can actually draw it. Imagine a metaphorical slinky for these red photons. Careful, I'm not saying the photon itself is actually zigzagging back and forth. This is just a way of representing it. Because I have crests on this diagram, I can actually say, well, the distance between these two peaks is actually 700 nanometers. If you look back with our unit conversions way back, nanometers actually stands for 10 to the 9. So I have 700 of these 10 to the 9 meters. The second you put this in your calculator, it will be 7 times 10 to the negative 7. That's perfectly okay because I don't just have 7 nanometers. I still have hundreds of nanometers, hundreds of a 10 to the negative 9. So that actually lines up with 7 times 10 to the negative 7. So again, the light photon here is traveling just in a straight line, right? It's just, we call them photons. Photons are little packets of energy. Photons have no mass. That's why we don't call them particles. Little packets of energy. These photons are traveling just directly straight. But just to represent the energy that they're carrying, each of these photons, I can represent them with a metaphorical slinky. It's not that it's really zigzagging back and forth, but the slinky would have had a lambda, a wavelength of 700. Then what distinguishes a purple photon from a red photon? Purple photons similarly are packets of energy. They also travel in straight lines. But when I do the sort of slinky relationship for this purple, I represent the amount of energy that it carries. The peaks themselves are actually a lot closer together. So in this case here, going from crest to crest, that distance there is only 400 nanometers. It's almost half the size. 400 nanometers, so this is going to be 4 times 10 to the negative 7. See if you can work that out for yourself. So it's going to be distance to distance, it's going to actually be less. In fact, what we're going to do is we're going to have an equation derived later on. This first equation here is going to be called the universal wave equation. This equation applies to all waves in general, whether it's water waves or light waves, as I'm doing here. We're going to see that the universal wave equation says the speed of the wave is actually equal to lambda f. In fact, we can actually derive this a little bit easier. I'll show you frequency in a second here. Wavelength, if you imagine you have a wave, the wave here is going to constantly move. So I'm going to wait for it long enough for this part of the wave to now overlap with the wave. The distance of the wave is exactly, it's traveled one wavelength, so that's going to be your d. Frequency, as we're going to see in a second here, frequency is actually divided by time. It figures out how many times you bob up and down. If I travel exactly a distance d, and it's going to be sort of per time for frequency, distance per time gives you speed, so that gives me the universal wave equation. So that's our first equation here, universal wave equation. I do want to explain to you frequency a little bit more, and then we'll just end off with one last question. Frequency here is a little bit harder to understand because instead of taking a still photo, instead of going down to the beach and just taking a picture of the waves as it looks at a given time, what I'm going to do is I'm going to imagine doing an experiment. I'm going to imagine I'm actually sitting in a boat out on the water waves. We already talked about here, the wave is going to just travel past you. And the question here, this time, is because I'm on this boat, I know I'm going to rock up and down. I'm going to figure out my sort of up and down motion here. So the part here that gets really fancy, I'm just going to do it down below so hopefully it becomes a little more clear. This is that still frame shot that we did. So still frame, I'm on a boat and I'm sitting right here. What I'm going to try to do is I'm going to try to plot this time. I'm still going to try to plot the y-axis. I'm going to still try to plot how far off the equilibrium line I am. But this time what I'm going to do is I'm going to plot it against time. So let's imagine I was on a boat, I'm on the rest line here, and let's say that's t equals 0. At a time of equals 0, I'm going to be at a distance currently of 0 meters off the ground. That's where I am. What I'm going to do here is I'm going to take another picture 1 second later. Maybe 1 second later, the wave would have pushed over a little bit here. Just going to sketch it here. If you have other colors, it would be helpful. Maybe the wave pushed over. When I'm on the boat, I would have rocked up with the wave. I'm actually a little bit higher when I'm at, let's say, t equals 1 second. So what's going to happen here is I'm going to find 1 second of time. I'm going to figure out that height, and I'm going to say, okay, at 1 second, I happen to be at that height there. Maybe a little bit later, I'm going to push over a little bit more. Maybe that's the part that I'm actually at the crest, right? And maybe that's going to be 2 seconds. At 2 seconds, okay, I matched up with the peak here. And what I'm steadily going to get here is going to be a curve. Well, in between those times, half a second, 0.8 seconds or whatever, I'm going to gradually go to the top. Then what happens? The wave here keeps pushing past you. I'm going to actually, following the wave here as it slid past me, I was at the top, and now I'm going to end up rocking downwards as this wave is pushing past. By the time on the green, I'm actually lower than. So in this case here, I'm actually going to be rocking lower than. I'm actually going to be at that time t, whatever time that is. I'm actually lower than the equilibrium line. And then finally, let's do one more. Maybe I'm sort of I already hit the trough here and I'm now rocking back upwards. I hit the trough and I'm now rocking back upwards. Eventually what you end up with, strangely enough, these are called sinusoidal waves. They just sort of rock up and down. It's like I drew the same diagram. But you want to be really careful here. This first diagram is a still shot. This first diagram here is displacement. It's sort of a still photograph of x and y. You cannot take a camera picture of this one, the second graph. The second graph here likewise says the height above the rest line, but this time here it's looking at your clock constantly. At this time, I was at the rest line. A little bit later, I'm rocking a little bit higher. A little bit later, oh, I hit the peak. A little bit later, oh, I'm coming downwards here. I can't actually take a picture of this. This one here is sort of tracking your bobbing up and down sort of motion. I had to draw this graph here. Coincidentally, it turned out to be very similar because I'm following this wave here as it passes by. Earlier, we had called this a wavelength when it was on the distance scale, when it was on x. But this time, what I can do is I can actually time how long did it take you to go from the peak. You're rocking from the peak all the way down and all the way back upwards. That's hit this time here. This one here is now a time. We're going to call that there the time for you to repeat itself. That time there is referred to as the period. We actually saw period back in kinematics. Again, I told you it made more sense in the wave section. Whenever we deal with periodic motion, motion that repeats itself, period is actually, if you look back earlier, it's the time for one cycle. So it still measures crest to crest, but this time, instead of measuring it in terms of distance, this time is measuring in terms of time. So period, they use capital T for it here. It's going to be unit seconds because it's time for you to rock up and down one full motion. The reason why we need this graph here is this actually helps us define frequency for us. Frequency is the reciprocal. So frequency, let's use F. Sometimes, unfortunately, they actually use the nu symbol. It's like a U with the tail. But frequency is the reciprocal of period. So frequency is actually, earlier we were waiting as long as you need for 1 second to pass. It could be split seconds. It could be minutes. In this case here, what we're going to keep constant is we're going to keep 1 second. Just imagine a nice ticking of the clock here. I'm going to imagine how many full cycles do I get in every second. So frequency is actually the number of cycles per second, and it actually tracks for you how many times you bob up and down. So back to our earlier example with this universal wave equation, when the wave here actually travels exactly the unit of one wavelength, so it overlaps with itself, it would have taken the time for one frequency or one period. So distance over time gives you speed. That's where that formula comes from. From these wavelength examples here, the red photon, if you were on a metaphorical boat, as the slinky here rocks up and downwards, the peak-to-peak distance is only 700 nanometers. It's actually fairly narrow. This wave here is going to speed past you. It's going to zip past you. And as it zip past you, you're going to hold on for dear life. You're going to rock up and down here many, many times. You can find the frequency, how many times you rock up and down, depending on how quick the wave is passed and depending on how much the wavelength, how far apart the crest-to-crest distance is. Compare that to the purple wavelength. Again, the photons are not zigzagging back and forth, but the metaphorical boat this time, the metaphorical waves, these ones here are actually a lot closer together. Because wave is going to zip by you at the same speed, and it's not taking that long for you to rock down and up like this, you're going to rock up and down way more times than before. So from this equation here, we're actually going to get a inverse relationship. Your speed is always going to be a constant. Your speed is set by what type of wave, water wave or light wave. And it basically says wavelength and frequency, wavelength and this sort of bobbing up and down, how many times you bob up and down, are opposites. They are inversely related. When one goes up, the other goes down, which shouldn't really surprise you. Going from the red to the purple, as the wavelength itself shrinks, as it doesn't take you that far to get from the first peak to the next peak, as it zips by you, the light is still going to zip by you at that same 3 times 10 to the 8 we did earlier, but because the crests are a lot closer together, we're going to bob up and down way more times. So those two are opposites. We're going to see in the next lesson that energy is actually proportional to frequency as well. So back on a universal wave equation, back when we were saying, yeah, high energy, we're actually going to also have the high frequency side on this side, and we're going to actually have the short wavelength side because wavelength is opposite to frequency. So more on that in the next lesson. So let me just finish off this lesson here just with a quick calculation. Just wanted to introduce you some of the vocabulary to waves. Let's just finish off with this question here. Let's imagine we have a sailor. So we actually are on a boat this time. A sailor finds it takes 2 minutes for 6 full waves to pass. So maybe he started tracking when he was at the top of the wave, he times it for 2 minutes, and he ends up realizing he rocks up and down full motions 6 times in this 2 minutes to pass. The question here is just asking you, I want you to calculate the frequency and the period for this motion. So as always, I just want to start off with a picture if we can. This time we actually do have a water wave. Maybe he starts his clock here when he's at the top of the wave. Over time, even though t equals 0, over time the wave is going to push past him. And as the wave pushes past him, he's going to end up just rocking down. As the wave continues past him, he's going to end up rocking back upwards. He's going to count 6 full down and full up motions. And it takes him 2 minutes to actually travel through this up and down motion 6 times. This is sort of like that pendulum example. You don't just need to time the time for just one motion, crest to trough and then back to crest. You can actually time a couple cycles just to average out some inconsistencies there, and you can actually figure out on average, if I rocked up and down 6 full motions and it took you 2 minutes to do it, you're going to find this calculation frequency period fairly simple. One thing though, when you actually look at the units, we're talking seconds for period as well as for frequency. So anytime you have minutes, the first thing you want to do is you want to switch it over to seconds. So I know 1 minute is 60 seconds, so we're talking 120 seconds. What I would do is I would just, because I know there's going to be a sort of reciprocal fraction sort of relationship, just take these two numbers and just divide the two numbers, just haphazardly, just randomly. So here's what I'm going to do here. I'm going to take my first number. I take 120 seconds, so that's going to be seconds on top. I get 6 full cycles. I do the math of it. I kept the numbers fairly simple here. 120 divided by 6 gives you 20, and my units are now going to be seconds for every cycle. Is this the period or is this the frequency? In this case here, when I say per cycle, I mean one cycle. I can write this out in words here. Well, 6 cycles took 120 seconds. That means one cycle took 20 seconds of time. If I give you an infinite amount of time, if you wait 20 seconds, this is actually the period. This is how long it took for one full from crest to the bottom back to the crest. So that's the period. To get to frequency, you may have done the division the other way. You may have done 6 cycles in 120 seconds. Like I said, just divide the two numbers just sort of haphazardly here. 6 divided by 120 gives you 0.05. The units would then be cycles per second. Again, you can write that in words here. I get 0.05. I get 5% of a cycle for every second that passes by, because frequency by definition is how many cycles pass by. This time, I'm not giving you an infinite amount of time. This time, I'm only giving you the time for 1 second to beat across. In this case here, for every second, you actually only manage to get 5% of a cycle, which is why it takes some 20 seconds for you to get one full cycle. 1 second is only sort of a part motion. You've only done maybe crest to a little bit lower down this way. This one here is going to be the frequency. Cycles is actually not a unit. So actually the unit we're actually saying is 0.05 per second. Per second can sometimes be written seconds to the -1, or better yet, we're going to actually use hertz. Hertz is going to be the standard unit, and hertz just means per second for us. So per second. Just to verify this relationship here, I had just randomly, haphazardly divided the two numbers just randomly. What you can do is just to show you frequency is the reciprocal period. You know when you take the reciprocal of a fraction. Let's take the reciprocal of the first fraction. It basically does the upside down. The reciprocal of that bottom number, I get the 6/120, and I get the 0.05 again. So that's going to be 0.05. Shorter the wavelength, the higher the frequency. The higher the frequency, you bob up and down more times, and actually the shorter the time it needs for a period. So just have a look at the lesson. Make sure you're familiar with some of the language, some of the vocabulary. We'll flesh this out a little bit more in tomorrow's lesson. Thanks, guys.